as I mentioned, so now we know how to calculate the death probability, survival probability for a given time interval using a given life table. Let's quickly go through this example and find the probability of these three cases using this uh, extracted life table. So in here, so unless in the previous example, I mentioned that, so unless we have more information about the cohort that we study, we have to uh, do some estimation processes to find the LX and DX on that uh, whatever the population that we are considering. So in here, you can see in this time lab table, we have decimal places for the number of survivors and number of deaths, because maybe sometimes they have created it for a large cohort like 1 million and then divided by 1,000 to have this number. So there is a possible explanation that we can have for decimals that we are seeing on the table, or maybe they have used kind of a different modeling technique to use with the data that they have collected and predict the number of survivors and the number of deaths for each time interval. So we don't have to worry about those things. So that means in here, the point is, at some cases, these numbers are whole numbers, but for some cases, we can expect decimals as well. So we just need to stick to the definitions of these probabilities and calculate the values, because after we build the time life table, we don't rely on the methods that we use to build the timetable, life table, but we use it to calculate different uh, probabilities as it is needed. So let's quickly go to part A, where we need to find the probability of survival of a person who is at age 20 and surviving for 5 years. And we can use the equation 1 directly. So it's 20 plus 5 over L20. And we can find the values. L25 is given in here. And L20 is also given, so that we can get the probability directly. And for the part B, it says the probability of death for a person who is at age 20 and the death occurs within the next year. So if you could remember, so we don't use 1 if we have it for 1 year time period. So that's why it's cube 24. And now we need the death probability. So we need the number of deaths from the table. Since this is 1, that means the number of deaths starting the 24th interval, which is the 24th year. And X is 24. So LX24 is the number of survivors were there at the beginning of the year. So we have these two numbers on the table. And finally, we have the probability like this. And for the part C, it says the age is 20. We need the death probability, but the subject has survived 4 more years from 20, and we need the probability of death occur after 4 years. That means if I get the age line starting from 20, they have survived for 4 years. Now they are 24, and now we need 1 more year. So the death occurs between 24 and 25, the time interval. So we need the number of deaths in between this interval. That is 24 again, because I said in this interval 24 is included, but 25 is not. So number of deaths beginning from 24 and goes to one more year. So we can put one here if you like want to make sure that it's one more year period, but no need to put one there. And then the starting age is 20. That's why we need L20 in here. So you can see the difference. So in here we had D24 and L24 because the age was 24. But in here, the death occurs in the same interval, but the observation begins at age 20. In here, the observation begins at age 24. So the number of deaths during that interval is same as the numerator that we use for the part B, but for the denominator, it's 96178 and 01. So that is how we can use these three equations directly and get the values. So I haven't included this deferred probability equation in here because it follows the same theory of the death probability definition, which is the probability of death for a person who is at age X and death occurs within the next T years. So at the beginning, it's easy if we can visualize the time interval using this time diagram. So then quickly we can select the corresponding numbers from the table. So that's a quick practice that we can carry out through these calculations. And this is a simple example of how we can use these numbers and tables accordingly. Now we can look into a different example. So in this example, says for a certain population of 20-year-olds, so we are given 3 points. 2/3 of the population are non-smokers and 1/3 of the population are smokers. So now, before giving any more information, they says that the population of age 20 has two distinguished categories, smokers and non-smokers. And then the future lifetime of a non-smoker is uniformly distributed over 0 to 80, and the future lifetime of a smoker is uniformly distributed over 0 to 50. So these are future lifetimes, not the actual age. Otherwise, we know that like the habit of smoking begins at somewhere in the life. So this says if that person starts smoking at age 20, so then for the next 50 years, this would be the lifetime and the expected, which means the highest value for the future lifetime for that person is 20 plus 50. But if someone start at 40, so then the highest value is 40 plus 50. But in here, for a non-smoker, it says 0 to 40. So we have to assume that. So then for this period also it's beginning with at some point of the life. So you may see that the starting point is important in this case. So, and that's why I may mention at the beginning as well. So we use these kind of impractical assumptions for the calculations, but these things gives the approximated numbers closer to the real values. So that's our target. So we don't need to get the actual value because we know that it's hard to get and we don't have the functions to get in practice. So we will make different kind of assumptions and approximate those values using these kind of assumptions. And these assumptions are mostly based on previous studies, and these numbers can vary with the outcome of those studies. In this question, so we are asked to find the survival probability of a person who is at age 40 and survives for 5 more years. That means starting from age 40 to 45, we need to find the probability of survival. But there's one additional condition. So this randomly selected person can have uh, uh, like that can fall into two different subpopulations, which is non-smokers and smokers in this case. Uh, so in here, so we need to find that probability for a life selected from those surviving to age 40. So that means, so if someone lives for 40 years in this population, so now for those individuals, we are calculating they are surviving, the event of they are surviving for 5 more years. So that's the um, like the story of this question. So different kind of things to think about. Let's say uh, we'll go through these points and think about a way to decode this information first. So in the first point, uh, we have to consider about like this. So this information is given for 20-year-olds. So we know that at this point they are 20 years, and if we had a life table, so our X would be 20 for most of the cases. But we don't have a life table up to now. And the other thing is, uh, so since we don't have a life table, it doesn't say that uh, like we need to calculate all the values in the life table to get it. But for sure, since they have specified about the population is 20-year-olds, so there is a possibility of using L20 for some calculations, because this is the corresponding number for the number of survivals of this population at the beginning of 20th year. So this number includes both subpopulations. And then we can incorporate this first point into the calculation. So our timeline at age 20, future lifetime starts at 0. So it goes like this. And at the beginning, we can say we have 2/3 of L20 for non-smokers and 1/3 of L20 for smokers. So if you sum up this, you get L20. So that is mathematically correct. And then for non-smokers, now we can think about these two subpopulations separately because we have two different future lifetime random variables. So distributions for the future lifetime random variables. For the non-smokers, we have a uniform distribution spans from 0 to 80, but uh, the point that we need to keep in our mind, so they are 20-year-olds at the beginning, but the probability we need to calculate starting from 40. So they have already covered 20 years into the future if we consider this lifetime. So we can calculate, so we know that the uniform distribution, it's easy to calculate the probability because it's the area of a rectangle and the total area is 1. So we can find the proportion of individuals who survives to age 40. It's like this. So in here, we have age 40. And to calculate this probability, first we need the proportion who survives through this period. And it is for non-smokers, I'll use NS. For non-smokers, we can expect So from 0 to 80, they have the future lifetime distribution. And out of that, they have consumed 20 years. And the entire area is 1. And since they have consumed 20 years out of 80 years, so this is the probability of surviving up to this point, which is the age 40. So we can say it's 3/4. And for smokers, again, we can use the same concept. So they are 20 and their future lifetime goes from 20 to 50 more years. So this is in terms of the TX. So their age is 70 and 100 respectively. And now from D20 to 20, again, the entire probability in this interval is 1, but they have consumed 20 years out of these 50. And this is the survival probability for that interval. It's 3/5. So these are the probabilities, but we can convert into fractions or percentages as per our need. And now we know that if we had some amount of non-smokers and smokers among this population number, as we have decomposed it into 2 parts now, non-smokers and smokers. So the amount of people from each subpopulation who has survived up to the age 40 can be found by multiplying the survival percentage from the number of people who has been there from the beginning. So which means at the beginning we have L20 in both subpopulations, but now we have decomposed into 2 subpopulations, and we know from each subpopulations after 20 years, this much of survivals or this much of percentage of survivals will be there. That means we just need to multiply the starting population of each subpopulation, or the population survivors of each subpopulation with this survival percentage. So at 20 and now at 40, so we have, initially we had this much of non-smokers, and after 20 years, we have to multiply this amount to get the survivors. And here initially we had 1/3 out of this number, but now out of this we lost 5, like 2 parts from 5th of the population. And so these are the survival numbers and at the end of 20 years. So now we have decoded it into 2 cases. And if we get this summation, so it tells us this is the total number of survivors at the beginning of the 40th year. So if we simplify this, we can see, we can cancel out this one. It's 0.5 and this is 0.2. So eventually we have 70%. Yeah. So non-smokers, like from the entire population, we have 70% of the people who are as the survivors after 20 years. So we know the individuals or subpopulation numbers and also uh, the complete population number by now. Now we can think about a way of combining these information uh, to find the corresponding probability. So now let's say among those who have survived to age 40, uh, so this present, so in here it's zero 0.5 and zero 0.2. That means if we had 7 units, 5 units of this population are non-smokers, 2 units of this population are smokers at the end of the 39th year, which means the beginning of the 40th year. So we know now the proportion of the population after 20 years from now. So initially, at age 20, it was 2/3 and 1/3 for this, but now it's 5/2. That means 5/7 and 2/7. And now we can move on to the next information part where we need to calculate the probability of surviving from 40 to 5 more years. So if I get that jump in here, age is 45 now. So this is the time interval that we are interested in. So this number should contains both subpopulations in this entire or the finite population. And like in the same way, we can define, since this is a uniform distribution, so at age 20, the property of the uniform distribution is like this. So if your x follows a uniform distribution with A and B, so then x minus d, given that x is greater than d, follows a uniform distribution with 0 to b minus d. So that is how this conditional distribution of a uniform distribution can be derived. So it's come from the distribution theory. And we can use that concept here. Since both of these distributions are uniformly distributed from 0 to 80 and 0 to 50, starting from 20. Now they have almost consumed 20 years from their lifetime. So it's like D is 20. So we have to remove 20 years from their future lifetime by now. So for the non-smokers, after 20 years, for non-smokers, we have a uniform distribution from 0 to 60 because 80 minus 20. And for smokers, we have a distribution from 0 to 30. So these are the two uniform distributions we can think of. So in the same way, I can find the proportions like this. So we have 5 years to count. In this uniform distribution, again, the entire area is 1, and they have survived 5 years out of the 60 years they have. So this is the proportion of survivals for non-smokers, and for them, they have 1 as the total area, out of which they have consumed 5 out of these 30 remaining years. And we have the proportion of survivals of these non-smokers who is at age 40 by now. And This is the condition. So this is based on the condition where they have already survived for age 40. So this gives you 5/6. So these are the two percentages of survivors from those who have already survived up to age 40. And now we can calculate. So in here, we got at age 40, the ratio for non-smokers to smokers were 5 to 2 in the population. And in here, we can find it to be like this. So from this ratio, now it has to be this much of portion we need to keep, and we have to eliminate 1/12 part of that portion out of this population. And here 1/6 part will be removed from the population as deaths. So without any other kind of cases, we can find the survival probability of this population from age 40 to 5 more years directly with this case. Because we know if we get the proportion, always both numerator and denominator contains L20. So we don't need to depend on that because we know we can cancel out. And eventually we are dealing with the ratios or the fractions. But with the same intuition we had in here, so initially we had 2/3 and 1/3, and then we calculate the proportion using this the survival proportion using these two future lifetime random variable functions, and then we can solve it using the ratio. So we know that from the starting part or the starting amount of the survivors at age 20, we had 2/3 non-smokers, and after 20 years, it reduced to 5/7. And after 5 more years, out of this part, there will be 11/12 fraction. So this is the ratio corresponding to the number of non-smokers who were there at the beginning at age 20 and now they are at age 45. Initially, we had from the entire population, we had 1/3 of the population as smokers. And out of that, after 20 years, they have reduced to the proportion of 2/7 from the entire population who were at age 20. So this is after 20 years, which is this proportion of the population of unsmokers and smokers. So it is in between the non-smoker and smokers. So this is the non-smoker part, and now we are calculating the smokers part. So after 40 years, out of the entire population, we have 2/7 fraction of the smokers with respect to the entire population. And out of that, there will be 5/6 fraction of survivors for the next 5 years. So these two numbers gives, so once we add up, it gives the proportion, so the percentage of the survivors at the end of 45 years, which is 25. So we have this common factor 7 here and 6 here. We can like 12/10. So both has the same numerator, so the denominator, and we can solve it like 55 and 12. So then we can cancel out some cases and eventually we will be ended up with this. So now you can see, so if we had to calculate, we could use L0 and so L20 and do the calculation to find L45 and divide it divided by L4, which means the ratio in between L45 and L40 to get this number. But without doing so, without relying on the equation, so we use the argument which is familiar to us. By arguing that, we use this the distribution theory property of the uniform distribution when it is uh, conditioned on the survival case and use it directly. So this is a different way of approaching finding the survival probabilities and death probabilities if we have this kind of a nice assumption, which is uniform distribution. So there are few distributions like this. So uniform distribution, as I explained it here. So once we condition on any survival event, still it gives a uniform distribution in the nice order. So there are few more distributions like this. There's a Pareto distribution, which is commonly used in life tables. It's also says that if X follows the Pareto, then if we condition it like this, the resultant distribution is also Pareto with a different parameter. And there's a distribution called exponential distribution, and it is a nice distribution which has a memory loss property. I think if you could get kind of a stochastic analysis course during your graduate studies, so you will find it is very useful when we are dealing with Markov chains. So because it only depends on the previous state, but if it is an exponential, no matter what the previous state, will follow the same distribution for the conditional distribution as well. So those are the nice distributions that we can think for future lifetime random variables for some cases different for some different populations. And luckily here, most of the time for the life, we are using the uniform distribution assumption. And I mentioned the exponential distribution and the Pareto distribution for your reference. But we are not going to test those distribution theory knowledge in this course. But you need to have this kind of distribution theory relations related to the uniform distribution in this course. So that's why I mentioned it separately in here. So using this, we don't need to stick to the equations, but still if we can build an argument with the intuition, we can find the final uh, survival probability like this. So this is also possible way of dealing with these uh, numbers. So in here, we didn't have any actual number. So we deal with this information, which is the sub ratio of the subpopulations were given at the beginning of age 20, and the future lifetimes of these subpopulations are given with respect to age 20. And then we interpolate it in between the future lifetimes and found the distributions for age 40. And then using this, as just assume that there were L20 number of people in this population at the beginning, and since the ratio was given, we could calculate the respective sub ratios for non-smokers and smokers. And since we knew the distribution, we could find the survival proportions of these smokers and non-smokers after 20 years. Then we could calculate the number of survivors at the end of 20 years. So if we could find the probability, we can just divide L40 by L20 to find the survival probability from 20 to 40 for the entire population. But we had to perform one step more to find 5 more years ahead. For that, we deducted another distribution for the conditional distribution, which is X minus D, which in here, it says we had initially X amount of future lifetime, but we have consumed D amount of lifetime from that future lifetime. And we know that after that D amount, we are still alive. So depending on that, our new future lifetimes will follow different distributions. But fortunately, we assume the initial distribution as uniform distribution. Eventually, the secondary distribution this conditional distribution became another uniform distribution. Because of that, it was easy to calculate the survival probabilities for 5 more years from 40 to 45. And then we could build an argument that from the population, from the beginning, we had uh, 2/3 part for the non-smokers, but at the 20 years of interval, after 20 years of interval, we have 5 out of 7 of that non-smokers. And during the next 5 years, we have 11 out of 12 uh, for the survival percentage. And we could carry out the same argument on the smokers. And once you sum it up, it gives for the survival proportion of these numbers with respect to the whole uh, population. But this number says for those who have survived up to 40 years, so this is the survival probability of surviving them for next 5 years. So this is same as L45 divided by L40. So now you can see we can use different kind of equations in different ways to find the survival probability. So now we are moving to the next important part of this lecture. So it's the fractional age assumption. In the beginning, I mentioned that um, so these tables are given as like annual numbers. So we assume that at the beginning of this year, we have this amount, this much of survivals, and during that year, we have this much of deaths. So we could sum it up or do some subtractions to find uh, the corresponding number of survivals and number of deaths for different years and different time intervals. And mostly in practice, so we need to find uh, the survival probabilities for uh, like fractional ages. That means what is the probability of surviving for 1.5 years? So in the previous case, we could find it for 1 year or 2 year, but we have to develop a different method to interpolate in between the first year and the second year. So to do so, we can have two different ways. The first one is the uniform distribution of death. As you have seen in the previous example, if you have the uniform distribution, it's easy to work with because we don't have to integrate that function. It's just an area of a rectangle. So if you know the two parameter values, so you can get the width of that interval, and 1/width is the density of that distribution. So for a general case, if we say X is uniformly distributed in between A and B, that implies if you have X and Fx like this, their density function, which is given like this, only defined for this interval between A and B, and it is uniform. It's at a uniform level of K, and K is 1/B minus A. So that is the definition, and it's constant over this time, and the area under this rectangle is 1. So that's the beauty of this distribution. So if you have this uniform distribution assumption, so we call in acronym we can use UDD. It's easy to work with, and we can say it's like this. We have the future lifetime Tx and the current lifetime Kx, and both of them are uniformly distributed for the next 1 year. So that means from X to X plus 1, we consider it as uniform part. And then X plus 1 to X plus 2, again, it is uniformly distributed. So for each year of time interval, uh, so we have this uniform assumption. So then the area, if we could create a rectangle in between the two closest years for 1 year time interval, the area of that interval is 1. So that's how it goes. And if I say it like this, suppose we have age x at this point, that means dx start at 0. And we know that from the definition of the curtailed lifetime random variable, we said that curtailed random variable is the integral part or the integer part of the future lifetime continuous random variable. And we had it like this. If 10, so this is equal to 10 if T10 was like 10.9, still K was 10. And if T10 was 10.1, still K10 was 10. So we only extracted the integer part of that part. That means for the next year of time interval, K10 is at a constant level. So that's the same idea we use it here. So after X years, let's say, yeah, let's use T for here. So from 0 to T years, and then after 1 year, T plus 1. So H is X plus T, and here X plus T plus 1. So the curtailed random variable, I'll write it from here. Start from 0, T, and T plus 1, as it is given for each interval. So 1. So that means whatever the value which comes up with Tx, it goes for 0 in this interval. In between these two, if you have these, so these numbers goes as 1. So that is the concept. So in here, for a time point in between T and T plus 1, we can say the death occurs in between these. Suppose it is S. Oh no, it's for survival. So we can use a different number randomly. Let's say B. After B, yeah, time length. And this B is a fraction in between 0 and 1 because the gap is 1 from T to T plus 1. And the death occurs at this point. That means the value of Tx is equal to T plus B. But the value of Kx is still T because we only get the integer part of this value. So if T was 10 and B was 0.5, so then Tx is here equal to 10.5, but Kx is 10. So that's the uh, situation. So we call death is at this time point. So now keeping those situations, since the distribution is a uniform one in between T and T plus 1, let's try to find a proper way to define this using the probability notation. And first, let's find the death probability of a person who is at age X during the next fractional year of R. So R is a value in between uh, 0 and 1, including 0 but not 1. So it's a fractional age. So using this diagram, we can say the Tx is less than or equal to R if death occurs within this interval. And then let's use like Tx. So we used it here. Instead of R, we use V. Let's keep it like this and say for that interval, we know that the distribution was like uniformly, we assume that it is uniformly distributed. So the random variable for uniform distribution is U. That is kind of a general rule that we use. So we know for sure this U is less than R. And the other thing is K in here. So Tx is less than R. So the Kx is equal to 0 because at age, so we are considering about at age x and for the interval of from 0 to 1. So because the starting point is k is equal to 0. And since they are independent, we can denote this joint probability as this. And we know this probability, and the probability of this one is it's coming from a uniform distribution, and this U follows a uniform distribution in between 0 and 1. That means this probability is R. It's a fraction itself. And this one is the probability of death of a person who is at age X and death occurs during the next year. So now you can see R is a decimal number in between 0 and 1. And we wanted to find the probability of death starting at age X, but only for a decimal number period, which is spanned from 0 to R. And it is same as because of the uniform distribution assumption in between 0 and 1. So we could get the annual or the death probability for that entire year period multiplied by that fractional number. So it's just easy. If you see any kind of an assumption says, assuming the future lifetime are uniformly distributed, calculate the fractional age assumption like this. We just need to multiply the annual probability or death probability for that 1 year time interval and uh, multiply it with the fraction that we need to find. So that is the reason behind this equation where the uniformity assumption valid for 1 year time period. That is why we had the uniform distribution from 0 to 1. Because suppose that even in the future examples, we will see that. So if someone wants to find a person is at age 20 and surviving for 1.5 years, that means since they are independent, we can decompose it like surviving from 20 to 21 and 21 to zero point 0.5 years. So then apply this 0.5 year death probability. You can find it using the fourth equation. So that's the practice. So that's directly goes to the probability. Now, so we know that since we have these life tables, we can calculate the same concept uh, for number of survivors at that time point as well. it's called the linear interpolation, because we know from 0 to uh, so let's take this time interval. So x, like in here, from t to t plus 1 time interval, and r is starting from here and goes to somewhere in here, and r is like this. And we know from the life table we can find the people, the number of survivors at LT, and here the number of survivors at t plus 1. So if the distribution is uniformly distributed in between these cases, and if you want to find this, the value at this point, so it's easy to remember. It says just the average. It means from here to here it's r, and the length is 1. That means from here to here is 1 minus r. So we just need to find the value at x plus, so here not x, we have t. So t plus r in here, and we can say the value at the survival's value at t plus r is equal to r times l t plus 1 and 1 minus r times l t. It's just the first proportion multiplied by the second, or we have an interval with LT and LT plus 1. So R is the distance from LT to the death point, and 1 minus R is the distance from death point to the next beginning of the next year. So you just need to find multiply the R with the next year survivors and 1 minus R with the current year survivors. It will give a linear interpolation for the number of survivors at this partial life on the lifeline. So that is a possible way of defining it. So it's kind of the uh, general way you can use. So let's go into a proof to get this done. So it says the survival probability of a person who is at hx and surviving for a fractional year of r. And we know that from the definition, so we can say it's that 1 minus the death probability of a person who is at hx, and death occurs within that small time period of r. And from the previous case in here, so we can write it like, so this part, we can write it like r times the annual death probability. So that is one possible transformation that we can do. Then we need to we need to deal with L, which means the number of survivors. If we could remember, so this is in general, this is the life table function we use for pxt. So to apply this one, we need to convert this q now into a known value of p. So for that, I can say r, and for this q, it is now surviving from x to 1 more year. It's 1 minus the death or the surviving probability from x to 1 more year. So if you 1 minus the survival gives the death probability. So we can extend it like this. So then we can have the survival probability from X to R is 1 minus R plus R times surviving probability from X to 1 more year. So remember that this R is a fraction between 0 and 1. So we have 1 minus R with us now. And now we can use this equation directly. So for this one, it's X plus R over Lx. And for this, it's Lx plus 1 over Lx. And if you simplify this, you will get the X plus R is equal to 1 minus R times Lx plus R times Lx plus 1, the same thing. So that is how we can prove it. So, but if you visualize it, it's just if you know the integer time points, then you just need to multiply the fraction you are interested with the future lifetime point, which means the immediate future integer in the timeline, and then the remaining fraction will be multiplied by the immediate past lifetime integer point. So that's why if you know you need to find Lx plus R. R is the fraction. So then 1 minus R of Lx and R of Lx plus 1. So it's the two integer values that contains, so that acts as the boundaries for this 1 year time interval. So those are the two equations, but you will get the idea of that those two equations quickly when we add it into a practical situation. So as I mentioned, let's say for an example, if we want to find the probability of 20-year-old surviving for, let's stick into the previous example, 20.5 years. So now we have defined this for only for 1 year interval. That is because of this. So these are independent cases. So surviving from 0, 20, and 20 plus 20, and like let's say for this 20 plus 20 plus 0.5. So we are interested in like, so this is a 20-year jump, this is a 0.5 jump. So these are two jumps, but in overall, we have a huge jump. So this is, so the large arrow is the jump actually we want, but we can decompose into two independent jumps, and we can say the probability of a 20-year person for 20 years and for the probability those who has already survived for 40 years, because now they have survived for 20 years, now the age is 40, surviving for half, and which means half of the year, so for 6 more months. So this is a joint probability. Since they are independent, we could multiply the individual probabilities. And this one, straightforward, we know we can, if we had the life table, we can find it like L 20 plus 20, which is 40 over L 20. And for this one, you can define it using L40 plus zero point 0.5. Now R is 0.5 over L40 and use this equation by substituting X as 40 and substituting R as 0.5 to get this value and solve it. That is a possible way of doing that. Or in the same case, we can keep this as this, because if you were given this probability as a function, so we can integrate the function and find this probability. Or if we could have the force of mortality, we know how to calculate the survival probability using the force of mortality. So both cases are possible. And now for the fractional age, it is defined for Q, but the probability is in P. So here we have the death probability, but the definition works for the, so this is for the survival. The definition works for the death probability. So first we need to write the survival probability using the death probability. And then we can apply the equation, which is 0.5 times the death probability for the entire year. So this is how we can apply these two equations separately in depending on the information we have. So if we had a life table, we goes with the linear interpolation. If we have a function or the direct survival probability value, we could go with this. And it's just multiplying R, but the concept is using the independent law. So let's apply this example for this uh, life table in here. So we are given a life table now. So in this life table, you will see we have again whole numbers, and it says assuming the uniform distribution of deaths in between the integral ages, uh, calculate the following three probabilities. Let's quickly calculate these things. First, Q 61. That means the death probability of a person who is at age 61 and death occurs within the next 0.2 years. So this is Qx directly, and we know how to calculate Qx if we are given this dx and lx directly. But it says the number of deaths from 61 to 62, which is D61, and divided by L61. So that is the direct approach of this, because we know it's 2 times from the equation we got. We can write it like this, and then it's 0.2 times this. So this is the equation. We have it in here. Here the t is equal to 1, x is equal to 61. So that's how I got it. And you have both values in the table. So we can substitute the values and get the corresponding answer. So you can do it by yourself. Or suppose we didn't have this dx. Then we have to deal with Lx only. So first we can write down this as this, and then we can write the life table functions like this, and For this, again, you can write down. So R is 0.2 now. This is the uniform assumption. It's L62 and 8 times L63 divided by, so L61, sorry, and divided by L61. So that is the uh, second way of dealing with this equation. So it depends on the information. Since we had both types, so I could use both approaches in here. So those are the uh, different cases that we can use. For the same amount, we can use both equations depending on the information. So that is a one such example for that. And for part B, it says at L60 and goes to 2.2. No, since we have these L's here, let's calculate not L60 uh, because it's just a demonstration that we have already done in the previous case. Let's get another probability. Suppose this is Q from 60 to 2.2, the same interval. Let's get it 60 to 2.2 years. Now, this is also a new application. So in my example in here, I showed to deal with the survival probability. But here it's the death probability, so we cannot apply that multiplicative rule directly for the using the independent case. We first need to translate this one into the survival probability from 60 to 2.2 years, and then I can apply that independent rule here, surviving from 60 to 2 more years, and those who have survived for 62 years now only have to survive for 0.2 more years. So this will give us, this one is L62 divided by L60. And for this one, again, L62 plus 0.2 divided by L62. And for this part only, we can apply 0.2 times L63 plus 0.8 times L62. So all these numbers are given in the table, so we can find the value. So that is a possible way for doing that. Or I can start from this part directly and using the first equation, I can write it like this. So I'm showing some all possible ways at this point because I'm only using this example. So you can think of the ways that we can approach the same problem in many different ways. So if you want to like use this first equation, then you need to use this fractional age into the survival age into the death probability again. And now it's like this. So it's become more complicated. So I want to show that. So you need to pick uh, the shortest path. If you could, like before writing down the equation first, just think about the approach first and start the calculation, because depending on the equation that you rely on, the path you have to get into the final answer will take more time. So in this case, so it's like this. And again, you can find these values using LXS in the table. And for this one, it's D 62 over L62. And for this one, it's L62 over L60. So now you can see for the same approach, so we can use it in two different ways using these two equations which is given in here. But the special thing is R is in between 0 and 1. So if you have something greater than uh, R, which is like this, like 2.2, but so here we got, uh, then first get the integer part out. We can take it out if we consider the survival probability, not the death probability. That's why I re uh, arrange this death probability as a survival probability and then apply that independent rule in here to get the to separate this whole life, which means the complete lives in here and the fractional lives on the other side. Then I can apply this fractional age assumption of UDD to get it done with LXS or QXS in here. So that's how we can work on. And now we can think about something more complicated. Um, let's go with this one. It's also about L. I think no need to think about L in this point. Let's find the probability of Q. I will get, yeah, let's, instead of that L, because I can explain another interesting point in here, I'll use the same table, but now I'm going to calculate the death probability of a person who has already survived for 60.8 years, 62.8 years, and the death occurs within the next 0.3 years. So this is this is the most like we can expect different kind of fractional ages, and out of all those fractional ages, this is the most complicated case that we can think of, because in both hands we have fractional ages, the survival age and also the future interval age. So let's think about decoding this. As I mentioned, so if we need to find that survival so we need to use the survival ages to get into the, so we use to these two equations, one minus the survival and the multiplication of individual probabilities for individual or the individual probabilities of two independent events. So those are the two cases that we need to solve this one. First, we write it like this. So this is true. Now we can get this part using this. So we know they have survived for 62.8 years. That means in the number line starting from 60, they have survived 0.8 years. And so I'm just thinking about this age like in this way. So I need you to think about this problem in the same thinking pattern. So that's why I'm decoding it into different parts. So this person has survived up to 62.8 years. That means this person was alive at 62 and survived for 0.8 more years. And that's true. And then, since they have survived up to that point, so we know that now the survival age is 62.8, and we need that person to survive 0.3 more years. So if we use these two independent cases, we can think the person was alive at 62, like this. At 62, he was alive, and after 0.8 years of jump, still alive, and I need him to alive for 0.3 more years, and this point it's 63.1. Throughout these intervals, that person is alive. That means this probability is equal to like 62 year of the age of the person is 62, the beginning age in here, and he has survived up to 63.1 years. So that is a possible way of thinking this. So the probability that we need to find is in here. And it can be found using two familiar cases. So in here, R is 0.8. In here, R is 0.1. So we know that if R is in between 0 and 1, we can directly deal with the equations we have. So that's how I decoded this question into something doable. So now I can apply my known equations under the UDD assumptions for this probability and this probability, then get the ratio, you will get this probability. So that's the technique. So, so in here, sorry, it's not 63 because the age is 63. The jump is 1.1. So now it's clear. So now let's find these two separately. So P62.8 is 1 minus 0.8 times Q62, or we need the number of deaths in between L62.8 and L62 and divided by L62. So this is a possible way of finding D62.8. So that is, we can find this probability directly. And for in this case, again, 1 minus 0.8 times for this one, it's 1 minus P62, and it says 1 minus 0.8, 1 minus L63, L62. So these are the two equations we can use. And for this, it's 62 to 63 and 63 to 0.1 more years. So this is L63 to 62 times for this one. Since it is survival, L63 plus 0.1 divided by L63. And for this one, we can apply L64 times 0.1 and 0.9 times L63. So from the table, we can find this and this. Therefore, we can find 62.8 to 0.3 more years, which means 63.1. Using this ratio from the complete age in here, 62, and surviving for the 1.1 case, divided by surviving from 62 to 0.8. So that is known value now, you can find the final value using this. And this will lead to find Q62.8 for this. And in general, so I can write down a new equation for this case. So if we want to find the survival probability of a fractional age like this, suppose this is S and this is R. So, and both S and R are between 0 and 1, but uh, S plus R is greater than 1. So if this occurs, so then we can write this probability like x2 S plus R and x2 S. So you can see x2 S and x2 S plus R. And to find this, so you will have to use again the uh, independent assumption and decode it like here. It was 62 to 1.1 years. That means 62 to 63, 63 to 0.1 years. Then you can use the usual equation again to find that. But if this was less than 1, that means still the summation is in between 0 and 1. You can use the same assumption in here because it's in between 0 and 1. You can stick to this and find this value. So I'll change this probability as 62.8 to 0.3. So we have found it on the other side. I'll share it with you after the class. And yeah, that's how we can deal with these kind of fractional probabilities. And yeah, so this is kind of a new derivation of these two equations, and it's coming through the fundamentals. But so in here, so we want to find something else, but we need to think ahead and go back and derive a new equation for this. So that's why I like visualize this event 62 to zero point 0.8, and from there onwards another 0.3. So these two jumps can be considered as a one jump of 1.1. So that's how I started this decomposition, and then I could find these two separately using known equations and could end up with these two probabilities to find the final probability we need. And then I summarized the equation that we need to use. This is kind of a common equation. So it's kind of an extension of the existing equation using the independence law and uh, the fractional age assumption under UDD. So we can use this uh, whenever we need it and make sure to check whether this S plus R is greater than 1 if you want to use this decomposition. If it is less than uh, this one, which means if it is less than S plus R is less than 1, so no need to use this one. You can just use this one because in this equation, so in this example, we saw that once we condition the uniform distribution, so we don't care about the survival situation. We just want the lifetime ahead. So that means in both cases, we have the uniform distribution. So you don't need to worry about S. You can just go with R because the conditional distribution is also a uniform distribution. So that's how we can use these things. Finally, we can discuss this point and stop for today. So we can carry out these calculations to find the density function for Tx and using the force of mortality from a life table under this UDD. So most of the time when you are given a life table, they will mention that this table is uh, prepared under the UDD assumption or any kind of another type of assumption. So they will let you know. And in the life table, apart from LX and TX, we have UX and some other expectations that we are going to calculate in future topics. They also have listed those things for we selected years. So in the upcoming chapters, we will like discuss about these new life table functions. But today we use the most basic and fundamentals of the life table and extended it to calculations of the fractional ages. Uh, and even under the fractional ages, we have two assumptions to discuss. Today we only discuss about the UDD, so we can carry out this discussion for the other assumption, which is called the constant force of mortality, which I have already mentioned at the time I was introducing the force of mortality. So you can see how we can work in that one as well. And in here, so the density function, since it is uniform, uh, so we need to consider the function for the entire interval from 0 to 1. That means as soon as you see a UDD assumption, so the density function for that fractional age for that given interval from 0 to 1 is just the death probability from X to the next 1 year. So that's the meaning of this. And for the force of mortality, of course, we know if we know the density function and the survival probability, we can define the force of mortality. So using that equation, so I could define the force of mortality as this. So according to our needs, we can use these two cases. So we have already used this one in some of our examples, and this was discussed under the survival distribution subtopic, the force of mortality. And you will see for the QX, we have used the equation in here. So that's how. So now you might have noticed that all the equations that we have discussed up to this point are needed to build the new equations in future under this topic. So all these things are interconnected, and everything advanced has uh, grown on top of what we have already learned. So with the time, it's get complicated, and but you need to like clearly see the pathways that we are coming. So then you don't need to like memorize all the equations at the first. You can deduce the equations by yourself, like we did in this. So we didn't use this equation directly. Instead of that, we use our basic reasoning and derived it using the fundamentals. So that's the way we can deal with these life tables and the equations. Otherwise, it's hard to memorize all these equations at first. But if you come from the beginning and building each equation by yourself with this reasoning, so then with the practice, you will see it's easy to calculate these quantities because after this, we are going to calculate the expected values. For that, we need the probabilities, and the practice will give you uh, the advantage of tracking the question quickly. So that's all for today. And yeah, I'll stop recording.